Good morning, children. Now we will see question number 8-4. So here it says 1 plus 2 plus 2 square plus dash 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 plus 2 to the power n minus 1 is equal to 2 to the power n minus 1 for every n belonging to natural number. Okay. So solution. Let Pn, so consider this statement as Pn. So 1 plus 2 plus 2 square plus dash 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 plus 2n 2 to the power n minus 1 is equal to 2 to the power n and here minus 1. So first thing is we need to show that this is true for n equal to 1. So I'll write for n equal to 1, left hand side will be equal to 2 to the power 1 minus 1. Okay. So for always n equal to 1, you have to take the last term, okay, where n is involved, and you have to substitute n as 1. So here we'll get 2 to the power 0, that is 1. And then right hand side will be 2 to the power 1 minus 1. So 2 minus 1 will be 1. Therefore, LHS is equal to RHS, and thus your P1 is true. P1 is true. Now next we have to assume that PK is true. So we'll write, now let PK be true. Then we have to copy the same thing. Okay. The only thing is your n will be replaced by k. Okay. So then 1 plus 2 plus 2 square plus dash 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 plus 2 to the power k minus 1 is equal to 2 to the power k minus 1. Okay. So give this as equation 1. Now we have to show that pk plus 1 is true. That means we have to show that 1 plus 2 plus 2 to the power 2 plus dash 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 plus 2 to the power k minus 1 plus 2 to the power k plus 1 minus 1 will be equal to 2 to the power k plus 1 minus 1. Okay, we have to show this. So see over here. Now 1 plus 2 plus 2 square plus dash 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 plus 2 to the power k minus 1 plus 2 to the power k plus 1 minus 1. Okay, equal to, now for this much I can write 2 to the power k minus 1. Okay, so we get 2 to the power k minus 1, okay, for this much, and this I have to write here 2 to the power k plus 1 minus 1. Okay, so we get 2 to the power k minus 1, and here you get 2 to the power simply k, because plus 1 and minus 1. Now here you can see that you can mention over here from 1, okay, for this part, and here you can see 2 to the power k and plus 2 to the power k, same, so you get twice. Okay, here you can see that base is same, base same, so power will be added. So you get 2 to the power k plus 1 minus 1. Okay. So this implies 1 plus 2 square plus dash 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 plus 2 to the power k minus 1 plus 2 to the power k plus 1 minus 1 is equal to this. So here you observe one thing, that your Pn was like this: 1 plus 2 square plus dash 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 plus 2 to the power n minus 1 is equal to 2 to the power n minus 1. Yes, this was your statement. So here you can observe that 2 to the power n, okay, whatever was here, same thing over here, okay, to the power minus 1. So here you can observe that 2 to the power k plus 1. So here you are getting 2 to the power k plus 1 minus 1. Yes, so you can see that this is nothing but this is pk plus 1 term, okay, statement, okay. So this implies that equal to 2 to the power k plus 1 minus this, okay. Therefore this p k plus 1 is true whenever pk is true, okay. You'll write hence by principle of mathematical induction Pn is true for all n belonging to natural number. Proved, okay. Now let us see question number 9.1. Here is saying, using the principle of mathematical induction, prove that this statement is true for all n belonging to natural number, okay. So solution: let Pn denote the statement 1 by 3 plus 1 by 3 square plus 1 by 3 cube plus dash dash plus 1 by 3 to the power n is equal to half times in bracket 1 minus 1 by 3 to the power n. Now first thing is to show that this is true for n equal to 1. So we'll write for n equal to 1, left hand side will be 1 by 3 to the power 1. So you're getting 1 by 3. And right hand side will be half 1 minus 1 by 3 to the power 1. So you get half, and here you get 3 minus this on this. So 2, you get 1 by 2, 2 by 3, so 1 by 3. So therefore LHS is equal to RHS, thus P1 is true. Now we will assume that Pk is true, okay, and using that we will show that Pk plus 1 is true. Now let Pk be true. Then we have 1 by 3 plus 1 by 3 square plus 1 by 3 cube plus dash dash plus 1 by 3 to the power k is equal to half 1 minus 1 by 3 to the power k. This is your equation 1. Now next is to show that pk plus 1 is true. Okay, that means we should be able to show that 1 by 3 plus 1 by 3 square plus 1 by 3 cube plus dash 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 plus 1 by 3 to the power k plus 1 by 3 to the power k plus 1. We should be able to show that this left hand side, whatever I have written right now, is equal to 1 by 2, 1 minus 1 by 3 to the power k plus 1. I should be able to show this. Okay, so let us see. Now 1 by 3 upon 1 by 3 square plus 1 by 3 cube plus dash 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 plus 1 by 3 to the power k plus 1 by 3 to the power k plus 1 is equal to half 1 minus 1 by 3 to the power k. So this I have written for this much only. Okay, and then 1 by 3 to the power k plus 1. So here you can write from 1. Okay, and next we can open this bracket, so we'll get half minus 1 by 2 into 1 by 3 to the power k, and here this 3 to the power k plus 1 can be written as 3 to the power k into 3. Okay, now if you consider these two terms, you find that 1 by 3 to the power k and 1 by 3 to the power k is common, so I can take that out. So I'm left with half minus 1 by 3. Simplify it, so you get 3 minus 2 upon 6. Half 1 by 3 to the power k, and here you are getting 1 upon 6. Now next you can write 1 by 2 minus 1 by 2 into 1 by 3 into 1 by 3 to the power k. So this 1 by 6 I have written as 1 by 2 into 1 by 3, same thing. Okay, now in these two terms you can see 1 by 2 is common, so I get 1 by 2. I'm left with 1 minus 1 by 3 into 3 to the power k. So I will get half, and here 1 minus 1 by, here you can see base same, so power will be added, so we get 3 to the power k plus 1. Okay, so we got 1 by 3 plus 1 by 3 square plus 1 by 3 cube plus dash 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 plus 1 by 3 to the power k plus 1 by 3 to the power k plus 1 equal to this much. Okay, and this is nothing but this is the statement pk plus 1. Okay, so 1 by 3, 1 by 3 square, 1 by 3 cube dash 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 1 by 3 to the power k plus 1 by 3 to the power k plus 1 is equal to this. Done. So we can write therefore pk plus 1 is true whenever pk is true. Hence, by principle of mathematical induction, Pn is true for all n belongs to natural number. Okay, so this is done. Okay children, so question number 9(2) will be your homework, and question 10(1) will be also your homework. So you will do these questions by yourself. Okay, I will be doing question number 2 for you. Okay, so see this. So question number 2, solution. Let Pn colon, then you write 1 by 2 into 5, okay, in denominator, then 1 upon 5 into 8 denominator, then 1 upon here in the denominator 8 into 11 plus dash dash plus 1 by here in the denominator 3n minus 1, 3n plus 2 is equal to n upon 6n plus 4. Okay, so this is the statement, and using the PMI, principle of mathematical induction, we have to show that this is true for all n. So firstly, for n equal to 1, your left hand side, so you can see this is the term which involves n, so you take this term and substitute, replace n by 1. Okay, so you get this 3 into 1 minus 1, and here 3 into 1 plus 2, so you will get 2, and here you will get this, so 1 by 10, and your right hand side will be 1 upon 6 into 1 plus this, so you are getting 1 by 10. So you can write therefore P1 is true. Or firstly you will write therefore LHS equal to RHS, thus P1 is true. Okay, now we will assume that PK is true, so we will write now let PK be true. So when I say PK is true, then we will have this. So here you have 5 plus dash dash is equal to n upon 6n plus 4. Okay, so but here we have to replace this n by k, so we should have k, not n. Okay, so let pk be true, then we'll have this, give this as equation 1. Okay, now we have to show that this statement is true for k plus 1 also. Okay, that means we have to show pk plus 1 is true. Okay, so we'll write now 1 upon this plus this plus this plus dash dash plus 1 upon 3k minus 1, 3k plus 2 plus, now in this term wherever is k, you just replace k by k plus 1 and write over here. Okay, so you get 3 times k plus 1 minus 1, and here 3k plus 1 plus 2. Okay, now from 1, okay, using equation 1, this much is equal to k upon 6k plus 4. So you can write this is equal to k upon 6k plus 4 plus 1 upon 3 times this, okay, and here done, okay. So actually here you can see that k for pk, okay, the right hand side what we are getting k upon 6k plus 4. So for k plus 1, so for k plus 1 we should be getting k plus 1 upon 6 times k plus 1 plus 4, we should be getting this, okay. So whatever you have written on the right hand side you should simplify, and at the end you should be able to get this, okay. So see over here we have k upon this, you can see 6 and here 4, so 2 is common, so I can write like this, done. And here open the bracket, so you get 3k plus 2, and here when you open the bracket you will get 3k plus 5, okay. So in the denominator, okay, for both the terms you will see that 3k plus 2 is common, so I can take that out. So you are left with k upon 2, and here you are left with 1 upon 3k plus 5. So 1 by 3k plus 2, and here simplify it, so you get 3k square plus 5k plus 2, and here you get 2 times 3k plus this. Here you can see in the numerator you have got a quadratic expression, so try to factorize it. So you get 3k square plus 3k plus 2k plus 2 upon 2 times 3k plus 5 this. And here 1 by 3k plus 2, so you get 3k, k plus 1, 2 comes out, k plus 1, and here 2 times 3k plus 5. Then 1 by 3k plus 2, and here 3k plus 2 and k plus 1, and here this. Then you can see that this 3k plus 2 and here 3k plus 2 cancel, so you are left with k plus 1 upon, and down you'll get 6k plus 10. So somewhere we have gone wrong, okay. This should not be 5. Let me check once. Okay, it's correct. Okay, here like in numerator we got k plus 1, so down also like we are looking for this k plus 1 upon 6 times k plus 1 plus 4. Okay, so we are looking for this. So here what we can do is we can write like this: 6k plus 6 plus 4. So we'll get k plus 1 and down we'll get 6 times k plus 1 plus 4. Okay, so now you can see that here we have got in terms of k, 3k plus 3k plus 1 minus 1, and here 3k plus 1 plus 2. Okay, so we got this equal to this. I can put this in bracket. So now you can see that this is your statement pk plus 1. Okay, so now you can write therefore pk plus 1 is true whenever pk is true. Whenever pk is true, hence by PMI, that is principle of mathematical induction, Pn is true for all n belonging to natural number. Okay, so this question is over, and for today this much.